Alright, so in this video we're going to be talking about limits, and more specifically we're going to be talking about limits of trigonometric functions. Okay, so trigonometric functions. So really we're going to be talking about mostly about sine and cosine, and since also tangent is a function of sine and cosine, we'll also be talking about that. So before we even get started with trigonometric functions, we just need to talk about what they look like, right? So we both know that the sine and cosine function, they look very similar. They're just slightly kind of offset from one another. So the sine function is going to look something like this. And as we know, it goes on and repeats forever, right? And the cosine function looks very similar. It's going to look something like this. And it also goes on forever. And really the important thing about the sine and the cosine function is that they are both continuous everywhere. Okay, so we're not going to really prove that, but you're going to have to take my word for it, and you're going to have to know that both, okay, both sine of x and cosine of x are continuous everywhere. Okay, and this is important because it's going to let us basically everywhere. Don't need this last letter. Everywhere. This is important that they're continuous everywhere because it's going to let us think of a limit for sine and cosine, and it'll basically be a limit that will pretty much always apply, kind of like we had limits that applied for our functions early on when we first started talking about limits, and we're going to use those kind of fundamental limits of sine and cosine to solve more difficult problems, to simplify them to a limit that we know exists and that we know the answer for. So the way this helps us is if I have the limit as x approaches a of my function sine of x, that is going to be equal to, okay, just sine at a. Okay, so if I want to see what the limit of sine of x is as x approaches some number a, all I have to do is plug in that number a into my sine function. Whatever the answer I get is, that's my answer. Okay, and similarly, okay, and since cosine is also a continuous function, we set that up here, we can say that the limit as x approaches a of my cosine function, cosine of x, that is just going to be equal to cosine of a. Okay, so pretty simple for sine and cosine. Now the problem is that tangent is not a continuous function. Okay, so tan x is not continuous. Okay, and you can kind of see that in the graph of tan x, right? It's a combination of sine x over cosine x, right? So when you take a look at that, obviously cosine x can never be 0 because it's in the denominator. Since it's in the denominator, we're going to have some sort of discontinuity, and therefore, because of those discontinuity and those vertical asymptotes, it's by definition not continuous. And so if it's not continuous, we ask ourselves, well, can we somehow think of a rule that works for tan x just like we have for sine x and cos x? Well, there is, and the way we're going to tackle this is we're going to rewrite it as a combination of sine and cosine, right? So we know that the limit as x approaches a, okay, of tan x, well, we know that tan x, we're going to rewrite the limit here, limit as x approaches a, we know that tan x can just be written as sine x over cosine x. Okay. And we know that with our limit rules, we can separate this into a limit in the numerator. So the limit as x approaches a of sine of x divided by the limit as x approaches a of cosine of x. Okay. And we just so happen to know what the limit is as x approaches a of sine of x, and we know what the limit is as x approaches a of cosine of x, right? So the one thing that we have here is that the limit as x approaches a of cosine of x cannot equal 0, right? So we know what the top is here, we know what the bottom is here, we just have that rule that, I suppose, can't write equal here, we should write this rule that cosine, or rather the limit as x approaches a of cosine of x cannot equal 0, okay? And therefore, what we can say here is that this is just equal to the top. Now we know that's just sine of a divided by cosine of a. Remember, we got rid of the limits here now because now we're evaluating this limit at a. But this still has the rule that cosine of a cannot equal 0. Okay? And so what that means is that the limit as x approaches a of our original function tan x is just equal to tan at a such that cosine of a is not equal to 0. Okay? And now the kind of ultimate part to this limit is, okay, well, when is cosine of some number equal to 0? Okay, so when does this happen? Well, this happens at positive or negative pi over 2. It happens at positive or negative 3 pi over 2. It happens at positive or negative 5 pi over 2. And you may begin to start seeing some sort of a pattern here of what numbers are showing up in front of the pi. And really what ends up happening is it's every odd number, and it's either positive or negative. Okay, and so we can generalize this and say that, well, when does cosine of a equal 0? Well, it equals at plus minus n pi over 2, where n is an odd integer. Okay, so this is when cosine of a or cosine of x is equal to 0, right? And if you draw a graph of cosine, you'll notice that. Okay, or if you just type it into your calculator. So these are our three kind of basic limits that we have to deal with. Okay, so we have this limit, which is the limit as x approaches a of sine of x, and that's just equal sine at a. We have the limit as x approaches a of cosine of x, and that's just equal to cosine a. And then finally, we have the limit as x approaches a of tan x, and that is equal to tan of a, with the given kind of caveat that cosine of a cannot equal 0. Okay, so those are our three limits for trigonometric functions, and those are kind of the limits that we're always going to refer back to when solving limit problems with trigonometric functions, and we're always going to try and simplify things down to sines, cosines, and tangents. Okay, so that's everything for this video, and I'll see you guys in the next one.